All right, buckle up, everyone, because today we are taking a deep dive into a seriously mind-bending topic, quantum entanglement.
Oh, yeah, this is one of those concepts in quantum mechanics that really pushes the boundaries of how we understand the universe.
Definitely. You know, I was looking at some of the sources you shared, and it's just wild to think about these particles being connected.
Connected across vast distances.
Yeah, like across galaxies even, and still somehow influencing each other.
It's almost like they have their own secret language they're using to communicate.
Right. And it's not just us who find it strange. I mean, even Einstein called it spooky action at a distance.
He did. He really struggled with the implications of entanglement, which is understandable. It challenges our everyday intuition about how the world works.
Absolutely. So to really wrap our heads around this, let's break it down. Where do we even begin with something like quantum entanglement?
Well, before we can dive into entanglement itself, we need to lay some groundwork in the quantum world.
Okay, sounds good. Give me a crash course.
First up, let's talk about superposition.
Superposition. Okay, I've heard the term before, but I'm not sure I fully grasp it.
So imagine for a second, you're playing a video game, and there's this character who can be in multiple places at once until you, the player, actually look at them.
Okay, I kind of get that. So they're sort of like flickering between those locations.
It's not quite flickering. It's more like they exist in all those places simultaneously in a blurry state of possibilities.
Whoa, okay, so it's not just that we don't know where they are. They're actually in multiple places at the same time.
You got it. That's a fundamental concept in quantum mechanics, and it's this blurriness that lays the foundation for entanglement.
Okay, I see. So how does superposition lead to entanglement?
When two particles become entangled, it's like their fates become intertwined. They're no longer independent.
So it's like they're connected by an invisible thread, no matter how far apart they get.
More than a thread. Think of it like two dancers perfectly mirroring each other's movements across a vast ballroom.
Okay, that's a great visual. But how do we actually know this is happening? I mean, it all sounds a bit like theoretical magic, right?
That's where experiments come in. And there's this really elegant one using photons that helps demonstrate entanglement.
Okay, let's hear about it. Photons, those are particles of light, right?
Exactly. So scientists can take a single photon and split it into two entangled photons. They then send these two photons off in opposite directions.
So now we've got two photons linked by this entanglement thing, but what makes it so mind-blowing?
Here's the kicker. When you measure the state of one photon, let's say whether it's vibrating horizontally or vertically, you instantly know the state of the other photon no matter how far away it is.
No way. So it's like they're communicating faster than the speed of light.
It appears that way, which, as we know, is supposed to be the universe's speed limit.
Okay, that definitely lives up to the spooky label Einstein gave it. You mentioned he came up with this EPR paradox to try to explain it away. Can you unpack that for us?
The EPR paradox, named after Einstein and his colleagues Podolsky and Rosen, was essentially a thought experiment. They were really grappling with this whole idea of entanglement.
And they weren't buying it.
Not entirely. They argued that if quantum mechanics was a complete theory, then we should be able to know both a particle's position and its momentum with perfect accuracy.
Okay, but I thought Heisenberg's uncertainty principle said we can only know one or the other with precision.
Precisely. So Einstein and his colleagues were saying, look, this entanglement idea leads to contradictions with what we know about the universe. They thought there must be some missing pieces to the puzzle.
Some hidden variables that we weren't seeing that were actually determining the states of those entangled particles.
Exactly. Einstein believed that this apparent faster-than-light connection had to be an illusion, and that there was some underlying mechanism that preserved the cosmic speed limit.
Okay, I get his skepticism, but if Einstein was wrong, how did scientists ultimately prove that entanglement was the real deal?
That's where John Bell, an Irish physicist, enters the picture. He came up with a brilliant way to test Einstein's hidden variables idea experimentally.
So it was a showdown between Einstein's skepticism and the weirdness of quantum mechanics.
In a way, yes. Bell formulated a set of inequalities, now known as Bell's theorem, and the idea was that if these inequalities held true in experiments, it would lend support to Einstein's view.
But if the inequalities were violated, it would mean entanglement was actually real.
Precisely. It would be a huge win for quantum mechanics. And that's exactly what happened in the 1980s when a French physicist named Alain Aspect conducted groundbreaking experiments.
So, Aspect's experiments showed those inequalities were violated. confirming that entanglement was not just a theoretical core.
You got it. It was a triumphant moment for quantum mechanics and essentially settled the debate. Entanglement was here to stay, and Einstein's spooky action at a distance was undeniable.
Wow, what a story. So we've gone from this mysterious connection to experimental proof. But is entanglement just a scientific curiosity, or can we actually do something with it?
That's where things get really interesting. We're just starting to unlock the potential of entanglement, and it's already leading to incredible advancements in technology.
Look what? Give me some examples.
Think quantum computers that can solve problems in minutes that would take classical computers millennia. Unhackable communication networks that leverage the very nature of entanglement for security and sensors with unimaginable sensitivity that could revolutionize fields from medicine to astrophysics.
Whoa, okay, that's a lot to unpack. But before we get into the nitty-gritty of those technologies, there's one source you sent that I want to dive into. You mentioned an essay that you thought was particularly insightful.
Yes, it's an essay titled Quantenverschränkung, Fernwirkung in der Quantenphysik, which translates to Quantum Entanglement, Action at a Distance in Quantum Physics, written by Jörg O. Schneepatt.
Okay, Schneepatt. What's his take on entanglement?
Well, Schneepatt's essay offers a really great overview of entanglement. He covers both the scientific aspects and the philosophical implications.
I was especially intrigued by how he dives into Einstein's skepticism about the concept. It's mind-blowing that even a genius like Einstein had trouble accepting this.
It really speaks to how revolutionary these ideas are.
Totally. So Schneepatt presents Einstein's perspective, but then also walks through the evidence that ultimately proved him wrong.
Exactly. And he doesn't stop there. He goes on to explore the profound implications of entanglement for the development of quantum technology, which is what we were just touching on.
That's exactly what I'm eager to hear more about. Schneepatt really captures the excitement and potential of this field.
He does, and he also acknowledges the challenges that lie ahead, which is important to consider.
Okay, let's dig into Schneepatt's insights and see where this deep dive takes us.
One thing that really stood out to me in Schneepatt's essay is how he frames entanglement as this triumph of quantum mechanics.
Yeah, it's easy to get caught up in how strange it all is, but it's pretty amazing that we've been able to actually prove these predictions through experiments.
Absolutely. And Schneepatt doesn't shy away from the philosophical questions that entanglement raises, does he?
Definitely not. He goes deep into some pretty heavy stuff like non-locality, causality, even the nature of reality itself.
Right. It really makes you think, if two particles can be instantaneously connected across vast distances, does that mean our understanding of space and time is flawed?
It's a mind-blowing concept. Could it be that everything is somehow entangled at some fundamental level?
That's a question that has puzzled physicists and philosophers for decades.
I bet. And Schneepatt acknowledges that there are no easy answers.
Yeah, he doesn't try to offer definitive solutions, but instead encourages readers to really grapple with these complex ideas.
Which I appreciate. It's more about embracing the mystery and asking the right questions. I also found it fascinating how Schneepatt traces the historical development of entanglement.
Yeah, he talks about how even some of the brightest minds in physics initially resisted these ideas.
It's understandable, right? It challenged their entire worldview.
Exactly, and Schneepatt does a great job of capturing that tension between the old way of thinking and this new quantum reality.
It's pretty remarkable that despite that initial resistance, the evidence eventually won out.
It really speaks to the power of scientific inquiry. And speaking of evidence, Schneepatt emphasizes the importance of Alain Aspect's experiments in the 1980s.
Right, those were the experiments that definitively proved entanglement was real. Schneepatt presents that as a major turning point in our understanding.
Absolutely. It was a moment when the spookiness became undeniable. What I find particularly exciting is how Schneepatt connects the theoretical and the practical.
Yeah, he doesn't just dwell on the strangeness. He also explores how entanglement is being used to create groundbreaking technologies.
He really highlights the transformative potential, especially in the field of quantum technology. He talks about how it could revolutionize computing, communications, sensing.
Okay, let's dive into those applications. You mentioned quantum computers. How does entanglement fit into that?
Well, picture this. A computer that can perform calculations not just millions of times faster, but exponentially faster than our current computers.
That's the potential of quantum computers. Sign me up.
Exactly. And entanglement is a key ingredient. Remember how we talked about qubits being able to be in a superposition of states?
Yeah, so instead of bits that are either 0 or 1, qubits can be both at the same time.
And by entangling these qubits, we can create incredibly complex systems that can solve problems that are currently impossible for even the most powerful classical computers.
What kind of problems are we talking about?
Think simulating complex molecules for drug discovery or optimizing financial algorithms.
So we could accelerate scientific discovery and
Yeah.
make smarter financial decisions.
Exactly. And there's even the possibility of breaking the encryption that protects our online data.
Okay, that's both amazing and a little unsettling, to be honest.
It definitely has huge implications.
Schneppad also mentions quantum communication, right? How does that relate to entanglement?
Imagine communication networks that are completely unhackable. That's the promise of quantum cryptography, and it relies on the nature of entanglement.
So instead of sending information through traditional channels that can be intercepted, we would use entangled particles.
In essence, yes. Any attempt to eavesdrop on a message encoded in entangled particles would instantly change the entangled state, alerting both the sender and receiver.
Wow, so it's like having a built-in alarm system for your messages. That's a whole other level of security.
It really is.
What about those ultra-sensitive sensors Shepard talks about? How does entanglement play a role there?
Well, think of sensors that are so precise they can detect the tiniest changes in gravity or magnetic fields, or even measure time with incredible accuracy.
So we're talking about potentially detecting earthquakes earlier or building more accurate medical imaging devices?
Precisely. Quantum sensors, powered by entanglement, open up a whole new realm of possibilities.
It sounds like something straight out of science fiction. Schneppert paints a pretty incredible picture of the future with all this. But he also acknowledges that there are some serious challenges. Right?
Oh, absolutely. He's very clear that working with entanglement is incredibly difficult. These entangled states are incredibly fragile.
And prone to decoherence, right?
Exactly. Any little disturbance can disrupt the entanglement. And that's a huge hurdle for building practical quantum technologies.
It's like trying to build a house of cards in a windstorm.
It's a great analogy. It requires a whole new way of thinking about engineering. We need to develop new materials, new control systems, everything.
Schneppert also delves into the broader societal implications of this technology, doesn't he? Like ethical considerations and potential economic disruption.
He does, and he emphasizes the need for responsible innovation. He raises important questions about privacy, security, potential job displacement.
It's a good reminder that we need to proceed with caution and think about the potential consequences.
Schneppert also stresses the importance of open dialogue and public engagement.
We need to make sure everyone has a voice in shaping the future of quantum technology.
Absolutely. It's not just for scientists and engineers to decide. It's about society as a whole, understanding the implications, and working together to guide the development responsibly.
Well said. I think Schneppert's insights provide a really valuable framework for those conversations.
I agree. He encourages us to demystify these complex ideas and make them accessible to everyone, which is crucial.
It's about fostering scientific literacy and encouraging a new generation of innovators.
Exactly. It's a call for collective wisdom and foresight.
So we can harness the power of these technologies for the benefit of humanity.
And ensure that this new era unfolds in a way that benefits everyone.
Well, we've certainly covered a lot of ground in this deep dive.
We've gone from this seemingly simple idea of connected particles to exploring all these incredible implications.
And throughout it all, we've had Jorgo Schneppert's essay as our guide.
His work has given us a lot to think about.
But I feel like we've only scratched the surface of what this phenomenon has to offer.
It's true. There's still so many unanswered questions and so much potential to explore.
And on that note, we're going to leave you with one final thought-provoking concept that Schneppert touches upon. Okay, we're back for the final part of our quantum entanglement deep dive. And things are about to get really, really weird. You know, we've talked about the science, the technology, even touched on some of the philosophical stuff. But now we're heading into territory where things get a little out there.
We're going to explore some of the more mind-bending interpretations of entanglement, ideas that push the boundaries of what we think we know about reality.
I'm intrigued, but also a little scared, to be honest. But hey, that's what makes these deep dives so fun, right? So hit me with it. What are we talking about here?
We'll be talking about parallel universes, the role of consciousness and ideas that might seem more at home in science fiction than in a scientific discussion.
Okay, you had me at parallel universes. Let's start there. What's the connection to entanglement?
Well, remember how we talked about particles existing in a superposition of states, being in multiple places at once until we measure them? Some physicists take that concept even further with something called the many worlds interpretation.
Okay, I think I've heard of this, but I always get a bit lost in the weeds. So is this the idea that every possible outcome of a quantum event actually happens, just in different universes?
You got it. Imagine every time a quantum measurement is made, the universe splits, creating multiple branches, each representing a different outcome.
So in one universe, Schrodinger's cat is alive. In another, it's dead. And this keeps happening with every quantum event.
That's the idea. Essentially, every possibility becomes real just in these different parallel universes.
So there's a universe out there where I won the lottery last week. That's a universe I'd like to visit. But, okay, how does entanglement fit into all of this?
Well, some physicists propose that entangled particles might actually be connected across these parallel universes.
Wait, so instead of two entangled particles communicating instantaneously across vast distances in our universe, they're actually interacting through some kind of bridge between parallel universes.
It's one way to think about it. Of course, this is all highly speculative, but it's an attempt to grapple with this idea of instantaneous connection that entanglement suggests.
Yeah, it's hard to wrap your head around. It really challenges our basic understanding of what locality even means. Okay, so parallel universes are pretty wild, but I know you said things get even weirder when we start talking about consciousness, right? What's the connection there?
This is where things get really tricky, and even Schneeppat is careful about treading too far into this territory. But the idea is that consciousness itself might be a quantum phenomenon, and that entanglement could play a role in how our minds interact with the world, and maybe even with each other.
So you're saying my mind could be entangled with other minds, or even with the universe itself.
It's a far-out concept, right? Some theorists suggest that entanglement might be the mechanism that connects our individual consciousness to a larger universal consciousness, like some kind of cosmic internet of minds.
Whoa, that's a pretty big leap. So if entanglement can connect particles across vast distances, could it also connect minds across space and time?
It's a question that a lot of people are asking, not just physicists, but philosophers and neuroscientists as well. But it's important to say that there's no scientific consensus on this. The evidence for these claims is still pretty limited.
So it's more about exploring the possibilities and seeing where these ideas lead us.
Exactly. It's about challenging our assumptions and rethinking what we think we know about reality, the relationship between mind and matter, the interconnectedness of everything.
I think that's a great point to end on as we wrap up our deep dive into quantum entanglement. We started with this idea of particles being connected and ended up exploring parallel universes and the nature of consciousness.
It's been quite a journey. We've seen how entanglement has moved from a theoretical puzzle to a potential driver of amazing technologies, and we've touched on some of the most mind-blowing interpretations that are still being debated today.
And throughout all of this, we've been guided by Jorgo Schneeppat's insightful essay.
Schneeppat's work really shows the power of curiosity and the importance of being willing to embrace the unknown.
And that's a message I think we can all take to heart, whether we're scientists or just curious about the universe. So to all our listeners out there, keep asking questions, keep exploring, and never lose that sense of wonder.